Welcome everyone to Electro Matic's virtual commissioning presentation. Thank you for joining us today. My name is Dave Madonis. I'm an application engineer with Electro Matic, primarily responsible for the support of Siemens industrial automation equipment, such as PLCs, HMIs, and networking, and also the Siemens PLM product software. Virtual commissioning and digital twin concept have become hot topics in the industrial automation community. Today we'll give you a brief tour of virtual commissioning with the NX MCD software, with focus on our MPM plastic injection molding machine. So our agenda today, we'll take a look at the MPM 55E overview. Will Beach, our project manager, will discuss some of the functionality of the machine and the benefits of using it. And we'll take a look at some of the core benefits to virtual commissioning and what it takes to make a digital twin. And we'll take a look at the software used, such as PLC Sim Advanced. We'll take a look at TIA Portal and how to launch an HMI simulation. We'll take a look at the NX MCD and how it's used for the machine kinematic simulation. And we'll take a look at how all this comes together to make a digital twin with hardware or software in the loop. Then lastly, we'll open up the NX MCD and we'll take a look at a live animation of our 3D model of our MPM machine. So to start off, I'm going to pass it over to Will Beach. He's going to give you a little discussion on the MPM 55E.
Hi, everybody. I am Will Beach. I'm the project manager for our injection molding product line. So what we have here is our Model 55E, which we consider to be a benchtop machine. We consider it a benchtop machine because its overall dimensions are 38 inches wide by 34 inches long by 96 inches tall. This machine gets used a lot in laboratories for large chemical companies and also for universities for teaching applications. These companies like this machine a lot just because of its small profile and ease of use and how quiet it is, being an all-electric servo-driven machine. This machine is capable of producing 25 tons of clamping force, and this is achieved through our unique V-mold design. We can also run a wide variety of parts or different size parts with this 25 tons of clamping force. We can also use many different types of materials because of our screw geometry that we can achieve. Our barrel sizes range from 1 ounce, which is our standard size, all the way up to 4 ounces. We also have a maximum temperature of 700 degrees Fahrenheit, which we can achieve, which can run almost all polymers on the market right now currently at a very stable temperature. We also offer different screw options, such as a mixing screw, so you can achieve better color distribution in your materials. The maximum mold size for these machines are 7 inches by 3 inches by 2.125 inches. This gives you the ability to make good small profile parts and also create test samples for a laboratory environment. So inside the Model 55E, it is controlled by a Siemens S7 1500 PLC with a TP900 comfort panel. It also has 4 S210 drives and then also 4 S1 FK2 servo motors, which drive all 4 axes of the machine. So that's a good little explanation of our Model 55E injection molding machine. And if you have any other questions, you can feel free to reach out to me here at Electro Matic. And now I'm going to hand it back to Dave.
So, the idea of virtual commissioning, how it's used, it uses software to evaluate the machine function by virtual simulation of all levels, typically without hardware, and that's the goal. There are several levels that need to be simulated in order to create the digital twin of the machine. First, we need a way to simulate the PLC controller. We also need a way to simulate the HMI or operator interface. And we need to simulate the interaction between the PLC controller and the mechatronics of the machine. Once you have these simulation capabilities in place, you can realize the benefits of virtual commissioning. Now, some of the core benefits would be to lower the risk of real commissioning by eliminating errors virtually. Most machine commissioning is done with the trial and error method, in which case leads to broken parts and other costly damages. And it would be reassuring to know that deploying your PLC program to the real machine would not cause malfunction. Also, it makes sense to test the system in the digital domain and break parts and deal with issues in a virtual manner and not physically. Also, you can test the machine sequence as the machine is being built to help speed up the development cycle. Train personnel before the machine is built. Here you can help prepare some of your personnel that will be deployed to various remote sites for startup. You can show them how the machine is supposed to function, how it's supposed to operate. They're ready to go when they get on site. There's been many times when I've been on startups in the past where the OEMs just don't have the proper personnel that have the knowledge of the machine, to be able to get the startup, function. And a lot of times these people end up having to call back to their main office and talk to their engineering or development teams in order to help assist them. So something like this, where you could create a digital twin, put it on a laptop, show those personnel how it's supposed to work and how it's supposed to function, would be a big benefit and save a lot of time in troubleshooting as far as startup assistance. Also, you can use the digital twin for promotional purposes. Here you can show the customer how the machine is supposed to function. Have them sign off on the functionality. Or maybe you have a machine that's got various different variations that you want to show the customer. So it's a great tool to show them the animation of the machine and the differences that you have between those different machines. So first thing, we need a way to simulate our PLC program. And with that, we use a product called PLC Sim Advanced. This is a Siemens piece of software. And what it does is it basically emulates the S7 1500 controller. Essentially, it emulates the real-world controller in just about every way. Here we'll download our PLC program to the virtual controller. It has all the same functionality, like I said, as the S7 1500 does. Also, here it's able to handle co-simulation using an application interface. So if you wanted to have your own Visual Basic program or C++ program or whatever you have, you can actually tie into the application interface and be able to model the behavior of your I/O. Also, with the PLC Sim Advanced, I think you can run up to about 16 instances on a single computer. So you can essentially have 16 controllers running virtually and sort of virtually network them together if you had a complex network. You can also tie multiple PCs together over Ethernet. So you could have one virtual controller running on one PC, another virtual controller running on another one, and tie them together over a physical Ethernet network and exchange data, interlock data, just the way your machine would be set up. The next thing would be is the validation of visualization. This is something that can be easily started within the TIA portal project. So if you have a comfort panel or some type of Siemens HMI or a PC-based runtime HMI, it's very easy to start the simulation within TIA portal. Just a matter of clicking on the simulation button on the top ribbon bar within the TIA portal application. So together with that and the PLC Sim Advanced software, you can run the HMI just as if it's a real world HMI on the machine. It will connect to the S7 1500 virtual controller in just the same way it connects to the real world PLC. It will exchange the same type of data. You have I/O data, data blocks, memory flags, timers, and counters. It works just the exact same way. The next piece of software is used to validate the mechatronics of the machine. And this is the NX MCD software. We'll use this to create the kinematics of the machine by using your 3D model. And here we can animate the motion of the various parts and assemblies with multi-body physics. You can simulate the flow of material through the machine. You can check for collisions between machine parts and material. This is all accomplished by using virtual sensors and actuators. All the animation is controlled and monitored by the PLC logic running in the virtual controller. So on the video that you see here, we have a sort of a pick and place machine. And these animations are basically created by various types of joints, animation joints that you create within the MCD package. And you apply those joints to these various assemblies. So you see here a sliding joint for the horizontal axis and vertical axis of the pick and place grabber bars. You also see a hinge joint on the base that's holding the parts in which the gears are being placed onto. So all this is being controlled by the PLC directly. You have also something called collision checks. So we can actually test out when various parts or assemblies collide with each other. We can sense that. We can send information back to the PLC, such as a bit, a Boolean bit, to indicate a collision has occurred. We can even look at force information. What type of forces have occurred between these parts, or maybe the material that's moving through the parts. All this information can be fed back to the PLC monitor and controlled by the PLC logic. So how does all this come together? There's two main solutions. We have something called hardware in the loop and software in the loop. Hardware in the loop allows us to take our 3D model, and we can bring it in from NX. We can also bring it in from SolidWorks, AutoCAD, CATIA. There's some other files that we'll take a look at later. And bring this in the NX Mechatronics Concept Designer. And hardware in the loop allows us to tie the NX MCD software package directly to third-party PLC equipment, such as Rockwell, Control Logics, maybe Omron, Mitsubishi, really just about any PLC. And we do that with OPC connectivity. So OPC has been around a very long time in the industry. And basically, if you have an OPC server, that OPC server has a front-end driver for your PLC. You can bring that data in to the OPC server, and the NX Mechatronics Concept Designer becomes an OPC client. And it can be an OPC DA client for data access, or an OPC UA client for unified architecture. But today I want to focus on is the software in the loop solution, which does not use any hardware at all. In this case here, we'll do the same thing. We'll bring our 3D model in. SolidWorks, AutoCAD, CATIA, NX, various 3D applications. We can bring the model into NX MCD. We can use the totally integrated automation portal along with step 7 for programming the PLC and WinCC for programming the HMI. And those will be connected to the PLC Sim Advanced. So both packages will communicate to each other, the PLC Sim Advanced. So PLC Sim Advanced has a direct couple low latency connection directly to the NX MCD package. Communicates in the sub-millisecond range. It uses something called a soft bus architecture. which is more like an internal communication bus right within the PC itself. This is how we combine all these and realize the digital twin. Just to add another package, this is an optional package called SIMIT. SIMIT allows us to model the I/O behavior, maybe things such as temperature, pressure. We can model those particular values, and it provides a co-simulation to the NX MCD package. If you have drives, variable frequency drives, serval drives, SIMIT will allow you to emulate the serval drive virtually. It allows you to pass the telegram information that you'd normally find between your controller and the drive. We would do that completely virtually between the PLC Sim Advanced and the SIMIT software as well. So this is an optional package that can be added in if you have certain functionality that you want to emulate on the machine. And we're going to have more links that will provide more detail about these products. We're going to send you a link package later on that's going to dive into more of the benefits and so forth of the product. What are the reasons for the digital twin? At least in our perspective, in our MPM machine, some of the core reasons that we looked at is we want to be able to train our development team on machine function. We also want to be able to use it as a training tool to help new hire engineers and show them automation and controls, be able to get them to start programming and understand how these products relate to each other. We also want to be able to verify PLC logic changes. We want to be able to verify, well, if the customer needs changes, we make those changes virtually, test out the equipment, and make sure it runs properly. We also want to be able to verify the safety of the machine. And two aspects to safety is I can verify e-stops, any kind of safety logic, safety circuitry, ProfiSafe communications to the drives, that all can be verified virtually. Also, this particular machine, it's dealing with very large pressures. It's dealing with very large forces between metal parts, high torques. We have servo drives that are running through reduction gearboxes, and that can generate tremendous amounts of torque and pressure. You want to make sure that you're not applying too much pressure, which could cause parts to break and therefore cause shrapnel or harm to somebody that's standing next to the machine. Also, we'd like to be able to promote the machine to potential customers. We want to be able to show them how the machine functions, also be able to provide a little bit of training on that machine. But the big kicker here for us is basically we broke parts. We broke a bunch of parts on the machine. And there's a little bit of a story to tell about this, and that is that when we got this machine in, it had some third-party controls on it. And we wanted to retrofit them to use Siemens componentry. So we ended up replacing the CPU with an S7 1500 controller. And we replaced the servo drive with S210 single-axis servo controllers. The logic was, semi-complete. We had to get this machine ready for demonstration in a few days, and there was really nobody around that really understood the machine at that time. So a few of the engineers, including myself, we kind of racked our brain trying to understand the sequence of operations of the machine. That was a big deal to us, and because of that, we ended up breaking some parts. We ended up breaking about bending a 3-inch metal plate called the thrust plate. We spun 2 thrust bearings in the plate. We damaged a ball screw. We bent the purge plate. And we also damaged the mold ejector bolts. These are 2 half-inch size metal bolts that snapped in half. Could you imagine being the guy that first hit the start button on the machine and broke something. But the whole thing here is that, you know, we use the standard old-fashioned trial and error method to test the machine. And we took a risk. And well, we lost on that risk. You know, we broke some parts. It really slowed us down. You know, the cost of the parts were quite a bit, but it took a long time to replace these parts on the machine. It would have been nice if we had a way to virtualize and break these parts in a virtual manner and know beforehand what we're getting into. This would allow us to hone in on specific parts of the logic, put the proper parameters in the drives for torque limiting, make sure the torque limiting logic was working correctly. So the old method, it got us through, but as a result, it really slowed us down. So it would have been nice to have the digital twin and be able to break these parts in the digital realm. I'd like to get into the MPM55 componentry and some of the assemblies here that we're going to be animating. This is just a first pass digital twin simulation that we looked at. Right now, we're just going to model the basic simulation of this machine, and eventually we're going to start to incorporate more of the logic in and get ourselves a true digital twin. But for now, what we wanted to do is just animate a few of these parts. The first is the carriage axis. That's a single axis servo motor running through a reduction gear. It moves the whole assembly up and down. And basically what it does is it moves the injector nozzle down to the mold and get it ready for injection plastic. We also have the injector itself. It consists of two individual servo axes running through reduction gearboxes with two ball screws. The injector axis will push the hot plastic through the barrel into the mold. And after that process has finished, we need to recharge the barrel with new plastic. So also we have the injector screw axis on here. And as the injector retracts, the screw turns on and it fills the barrel with new plastic pellets from the hopper. So overall, we have 4 axes that we're going to be simulating. So right now, what I like to do is like to switch over to the NX MCD software. Just give you a little bit of a tour of the software and the toolbars and take a look at the model. First I want to show you is under File, we can open different types of models, parts files. Here we have our part file here, which is the NX default standard part file. We also support third-party files such as CATIA, SolidWorks, and some other industry standard files like JT files, step files. The SolidWorks file, just to mention, SolidWorks uses the same Parasolid kernel as Siemens does. So it's actually licensed by Siemens to SolidWorks. So when you use SolidWorks, you're using a piece of the Siemens technology in that. So that imports directly in without issue. Some of the things we have on our toolbar here, there are some detailed information about the Mechatronics Concept Designer. We have some default values here. We can adjust the acceleration due to gravity. We can change the direction of gravity here. We can also look at different coefficients of friction parameters, linear dampening, angular damping. Our physics engine, we can also be able to fine-tune some of the runtime parameters for collisions and the physics engine time slice sampling. At the top main tool ribbon here, we have our mechanical group. Here we have something called a rigid body, object source, object sync. These are some of the few that we're going to be using in the MPM machine. Here we have collision bodies, transport surfaces, using collision bodies in our application. We have different types of joints that can be applied to the parts or the assemblies, such as a hinge joint, which gives you a 360-degree rotation, sliding joints, cylindrical joints, screw joints, and so forth. From our electrical group, we can define different sensors to detect the position of parts or when parts collide with each other. We have a position control, we have speed control. These are applied to specific joints, so we can provide a position value to a certain joint and have it move to that position. Such as speed control, also we can change the speed or the velocity of some of the parts. We also have force and torque control. You can also apply a force or a torque to various parts to simulate that particular function. We have an automation group here, which is mainly for motion. We can generate motion and cam profiles. We can interact with numerical control units. And we have a design collaboration group, which allows us to export data to third-party applications, for further types of processing. Over on the left, we have our resource toolbar. Our physics navigator, this is used to manage all of our animations for the model. We have a physics group, joints and constraints, materials, couplers, sensors and actuators, runtime behavior, signals, signal connections. We have a runtime inspector, which is used during simulation of the model. Runtime inspector, we can add in various parts, joints, position or control information, and we can monitor that information here as it's running. And we can also change the values here as well. We can change Boolean type values. We can change the positions or velocities as integers or double integers. We can look at all that information here. We have an assembly navigator, which shows us all the various parts that we have on our model. And here we can turn on and off parts, hide them if we wish, break them out and look at them. And we also have a sequence editor. The sequence editor allows us to actually animate the model without any PLC connection here. So we can animate the model and create a step sequence of the various assemblies and how we want them to react. Okay, so let's take a look at our physics navigator. We'll take a look at some of the assemblies that we're animating here in the MPM. The three main assemblies that we're going to be looking at is the injection barrel, which is part of the carriage assembly. As you see it here in orange, this is a group of parts that we created when we created what we call the rigid body. When we create the rigid body, we bring up that function and we select various parts that we want to be part of that particular rigid body. The rigid body allows us to define a mass or a weight to these objects. Or it can be automatic detection based on the dimensions of the part and the type of material that's being used for that part. Once you've defined the rigid body and defined the mass, what you're doing is you're telling it to react to gravity. So it's going to respond to gravity just the way any normal item would in everyday use. We also have our injector screw here in orange. And again, that's going to be used to recharge the barrel with fresh plastic. And it's also going to be used to inject the plastic into the mold. And then we have our injector assembly, which has the two servo drives. And that's going to be moving also to inject the plastic in utilization with the injector screw. Joints and constraints. We have different types of joints that we've applied to these assemblies. In our particular case, we use a carriage sliding joint. We take a look at that. We have the carriage assembly here in orange. That is going to be a sliding joint. The sliding joint is going to be controlled by the PLC directly through variables that we're passing with the data block. We also have the drive hub injector, and that is the main servo shaft with its pulley. We also have the actual injector assembly itself. That's going to be a hinge joint because it's going to be spinning between 0 and 360 degrees. And we have a sliding joint for the injector barrel itself. So what we do is we have these joints defined between the assemblies. Now we have to provide a way to control these joints and be able to tell it what's the velocity of these objects and what is the position we want them to move to. So we have something called a speed control. And the speed control here is going to be used to change the speed of our servo drive. And the speed is going to be directly referenced to a tag in the PLC. We're going to have logic that's running to that tag telling it what velocity to spin this shaft at. Now you can see here that we've coupled the servo drive shaft over to the injector screw shaft here through a cog belt. So those two shafts are coupled with what we call a coupling gear. So a coupling gear allows us to specify a gear ratio between these two. So we have a 1 and we did it to 0.492, which was the gear ratio that we've used. So the master is actually the servo drive shaft. The slave shaft is going to be the screw injector shaft. So we specify those two here just by clicking on these particular assemblies. And our carriage sliding joint is controlled through a position control as well. And that is going to be also handled by the PLC logic. So we're going to map a tag directly to the position that we want the carriage to move to. So we've defined our joints and constraints between the assemblies. We've specified the methods of how we're going to control those joints. Next is we need to take a look at the signals. And what we do there is we create something called a signal adapter. The signal adapter is essentially our PLC signals that we'd like to use and connect with the NX MCD package. Let's take a look at the signal adapter. There's going to be 3 main sections of the signal adapter. Let's get this resized. And the first section at the top, this first section at the top right here, we're going to define local tag names that the MCD package is going to use, and it's going to be mapped to specific parameters of our sensors and actuator section here. So for instance, we have a carriage speed right here. This is the position control for a carriage sliding joint. And it's a speed parameter. So once we click on the carriage sliding joint actuator, over here in the right-hand corner, we have various parameters that we are able to control or read. It defines it right here. So in this case, you click on speed, and then you add that to the list. And you give it a specific alias name, or what I call a local tag name. In the middle here, we have our actual PLC signals. In our case, we're going to be using a data block. So I've created a data block in the PLC logic that's going to be used nothing nothing else except for passing, reading, and writing MCD control signals. So I've created these few tags in the PLC. I want to be able to control the speed of the carriage. I want to know when it's retracted or extended. I want to be able to monitor the motor torque, carriage position, hold pressure, injector speed, injector position, fill speed. I want to be able to read back from the NX MCD package what the actual carriage position is and what the actual injector position is. I'll be using a few of these in the demo here that we're going to run in a minute. How do we tie the PLC signals over to these MCD signals here that are controlling these speeds and positions? There's a formula section here that allows us to do that. For the carriage speed again is a local MCD tag. I'm doing a one-to-one assignment directly to the PLC tag called carriage speed up and down. Here I'm providing the velocity. So as the value changes in the PLC control logic, it will be mapped directly to the carriage speed in the MCD, which in this case, it's going to provide the speed information for the position controller. And I also do this with other various values, such as the position, the injector speed, the injector position, the screw speed. And I want to be able to read back the carriage actual position. So I map these as a one-to-one ratio. You can also make a formula over here. You can add in different expressions. You do all the standard expressions such as multiplication, division, add and subtraction. Even complex formulas can be added in here to be able to change the values and manipulate the values. So essentially, this is the signal adapter. This is how we map the PLC signals directly to our assemblies and how we make them move and how we animate those particular parts and assemblies. In order to get the PLC data in, be able to map these tags and be able to create the signal adapter, you have to make a signal connection first. We have a signal connection section down here. This is basically showing the different tags that I have selected for mapping. If you take a little closer look at this, signal mapping is basically a collection of the tags that I wish to use for this particular project. So over here on the right, these are the various external signals that I have mapped from the PLC and are brought in and now are making them available to use for the signal adapter. And what we basically do is we create this signal connection. And what we have is a signal connection here to our NPM machine, which essentially is our PLC Sim Advanced software running our instance of the NPM machine, which is basically our S7 1500 controller. This right now is running. The program is downloaded to it. What I can do is I can define what type of information that I want to read or write to in the PLC. Over here we have an option list. Here we can read our I/O, memory bits, input outputs, memory bits, counters, timers, a combination of these types of variables. Here we have data blocks, I/O and data blocks, and so forth. We can pick something specific that we'd like to read here. We can also go ahead and filter what specific data blocks or I/O that we'd like to bring in. Once you decided what you want to use, you update the tags. It goes out, MCD goes out and reads the database within the PLC controller. And it brings back all the available tags and data blocks that I can possibly use. And in my particular case, I have a lot more data in here that's used for control data, but I've only selected some of the variables that I wish to use in the application. You have a little green check mark here, which is basically the selection box. So I have plenty of variables here, but I'm only reading just a few of these for the demonstration today. So once you've selected these boxes, you go back to the signal mapping chart. They'll appear up over here. And basically, you can just click on these and you can create the pair signal, which basically just adds these to the signal adapter. That's our MCD signals that we have over here on the left. And down here, it shows the actual mapping of your signals and how they're set up. You have read signals, you have write signals, defined by the arrow that you see here. Other ways of doing this is you can also export a tag database directly from the TIA portal Step 7 package into an Excel file, and you can import the Excel file in, and it will help create the signal adapter for you without going through some of the steps I just showed to you. So there's a couple different ways of getting the data in and mapped correctly. Let's go ahead and run the simulation of what we have so far. I have running right now the PLC Siemens Advanced software. I also have some logic. This particular case, I made an S7 graph package. This is to just, maybe you've heard of S7 graph. It's based on the graph set language, which is a step transition software package. And this allows us to just provide the main sequence of operations. Each step basically sets a flag bit in the controller. And then from there, I have additional logic that reads that flag and does other further processing. Once the processing occurs for each section of the machine, it moves on and follows to the next step. And we also have our HMI. In this particular case, I have an HMI running, and I just have a simple cycle start button. I want to start the sequence of operations for the machine. So right now, I'm going to go ahead and start the simulation in the NX MCD software. Zoom out here a little bit. So we have our HMI running, we have our PLC logic running, and hopefully we can start the cycle. So you can see how the step transition graph set coincides with the animation of the model. And what you're seeing probably on your WebEx screen is probably updating about 1 frame per second, so it might look a little bit choppy, but if I zoom in a little bit closer here, run it again, get a little more of a detailed view of this. So you can see how I've basically emulated the cycle of operation of the machine. I've been able to incorporate logic. One more thing, I'm getting close to our time frame here, so let me just show you one more thing on the logic part. I have some additional carriage logic that shows you how I actually read the position that's being fed back from the NX MCD software into my data block. Here we have our MCD interface, which is our carriage axis. Here I'm reading the actual position of the carriage. I'm using that information to tell me when I have finished with the movements and to follow with the next sequence of operations. So when I start the cycle, you can see the values change at the top. It goes between 0 and 33 millimeters is the movement. So here I'm writing information and I'm reading information. You can read all different types of values. You know, we have a, for to take a look at this, we could monitor, let's see, we'll pick our carriage sliding joint. I want to show you the runtime inspector here. Stop this for a second. So here we have our runtime inspector. I've added a few of the sliding joints, the position control information to the runtime inspector. We'll go ahead and start the simulation. You should be able to see some values change here. We'll go ahead and run it one more time. Here's the speed of the carriage axis here. And there is the position. This will start when the carriage retracts. You can see it changing. So you could actually really run the entire animation model without the PLC connector. You can actually test all this out before you connect it, the signals. That's all we have for today. We'll probably have some ongoing seminars, webinars, maybe some videos showing you some additional function and features of the product, maybe some how-to demos later on. We're going to include a link package to show you some additional details on the benefits of virtual commissioning and some of the technical details about the Siemens software and PLC Sim Advanced as well. We appreciate your time. And we have a contacts page here. If you have any questions, please feel free to give us a call or drop us an email. So again, I'm Dave Madonis. I'm application engineer. Will Beach is our project manager for the MPM machine. Nick Steffes is our business development manager. Nick handles a lot of the commercial decision making. Please contact him for any type of pricing, demos, any information that you're looking for. Any technical questions, you can funnel over to me and Will Beach. We appreciate your time. Thank you very much.